Okay, welcome everyone. My name is Tim McDevitt. I'm a part-time developer on the visualization team at Wolfram. And today I'm going to take you on a tour of the complex visualization functions that are new in version 12. All right, so anyway, so here on the left is a picture from Maxwell's treatise on E&M in 1873. It's a picture of a capacitor. The two parallel lines there represent a capacitor along with electric field lines and equipotential surfaces. And so the picture on the right is a recreation of that using complex contour plot. And this is easy to generate with just a few lines of code. And so I'm going to show you this as well as a number of other things. So the new functions in particular are listed here. Some of them are new in version 12.0, some in 12.1, and then 12.2 we'll see ComplexArrayPlot for the first time. So the first function I'm going to talk about is ComplexListPlot. This works much like listplot, except that the data are complex valued. So here you're just looking at 50 random values sort of in the unit square in the complex plane, and it basically does what you think ComplexListPlot would do. A nice application for this might be if you're looking at the eigenvalues of a matrix. Frequently they turn out to be complex valued, and ComplexListPlot is a nice tool for that. Here you have an example of a 500 by 500 matrix with random entries uniformly distributed on -1, 1. And you can see the eigenvalues all live inside of a circle. So this is sort of a famous circle law for random eigenvalues or eigenvalues of random matrices. Another nice application that I like is being able to label eigenvalues with their corresponding eigenvectors. So here we have a 3 by 3 Fourier matrix. Compute the eigenvalues and eigenvectors using eigensystem. And I make what I call images here, but it's basically just a matrix form of the eigenvectors. And then using ComplexListPlot, I'm able to display the eigenvalues very easily in the complex plane, along with labels showing the corresponding eigenvectors. All right, and then just for fun, I also change the theme. So I think that's a nice application. And if you're solving an equation or a system of equations, you might have complex solutions. So here's one, sine of z cubed minus 1. This can be solved basically by hand, but solutions look like you see here in the picture. I made them the dots into stars just for fun. I want this to sort of be a memorable figure because I'm going to return to this problem when I discuss ComplexArrayPlot, so I want you to remember this. So I made everything sort of red, white, and blue just so it sort of stands out. Notice that all of the solutions to this problem live on one of 6 rays emanating from the origin. So there's 6 different angles here that correspond to solutions of the equation we're looking at, which isn't terribly important, but it's sine of z cubed minus 1 again. And then I've also highlighted some of the options that are sort of distinctive to ComplexListPlot as opposed to listplot, in particular the ones that begin with the word polar. So polar axes, polar ticks, polar axes origin, polar grid lines. In a complex context, things are often sort of origin centered, and a lot of times it's nice to be able to sort of use these sort of polar features. So anyway, for this picture, remember that the solutions, there are just 6 different angles, but there's an infinite number of solutions along each of the spokes sort of emanating out from the origin here. Okay, the next function is reimplot. Reimplot takes a function, well, the input is a real variable and the output is in general a complex variable or a complex valued function. And so you can see on the left, we have a standard plot of the arcsine function, which, the first time a student runs into this in pre-calculus or trig class or whatever, they're told that this is only defined from -pi/2 to pi/2. And if you construct the plot with the plot function in the Wolfram language, that's what you get because it ignores anything that's non-real. However, if you use reimplot, plot the same function, you can see in the middle of the graph, it looks the same from -pi/2 to pi/2. But the reimplot plots the real part with the solid curve, and then the imaginary part either dotted or dashed there. Right? And so you can see the sort of extension of the arcsine function out of the -pi/2 to pi/2 interval. And so it's just a little bit more, the output's just a little bit richer than it is with the regular plot. And so sometimes that's helpful. So one time that's helpful is, say, if you're working with Fourier transforms. So Fourier transforms themselves can be purely real or purely imaginary, and sometimes a mix. So this particular Fourier transform is mixed. So you can see with reimplot, you can easily see both the real and imaginary parts quite clearly. And then with plot labels, you can label the two components. You can also do the labeling with a legend instead. So plot legends goes to automatic, gives you the corresponding labeling. And then I'm also showing you here two distinctive options, reim style and reim labels. So reim style allows you to style the real and imaginary parts of the function. And then reim labels allows you to change the way the labels are displayed. ComplexArrayPlot is sort of similar to reimplot. It's a complex valued function of a real variable. And so again, here we use arcsine as an example. So on the left, you have the standard plot of arcsine of x, and on the right, you have AbsArgPlot. AbsArgPlot plots the modulus of the function as a function of x. So that's why it's always positive. And then it colors the curve by the modulus of the function, all right? And the colors are indicated in the corresponding legend. So you can see in the legend where the angle is 0, the color is red. And then like where the angle is pi or maybe minus pi, it's like cyan or something like that. So if you look at the regular arcsine plot where it's real and positive, it's plotted in red in the AbsArgPlot. And where the regular arcsine is real but negative, it's plotted in cyan in the AbsArgPlot. Okay, and then elsewhere, the arcsine function is not purely real, and so you get more colors then. Okay, so sort of similar functionality as reimplot. And again, this can be helpful when you're working with Fourier transforms. Oftentimes with a Fourier transform, what we usually plot is just the magnitude. So you can do that very easily with AbsArgPlot, but at the same time, you don't lose the angle information because it's present there in the color. Okay, next up we have ComplexPlot and ComplexPlot 3D. Here we have a complex valued function of a complex variable that we're trying to represent. And so sort of have a two-dimensional input and a two-dimensional output, and we need to try to represent that in a two-dimensional image. So what we do is we take the domain of a function or a subset of the domain of a function, and we color it by the argument of the function value at each point, right? So if you look at the first image on the left, you see where all the colors sort of come together at the central point. So when that happens, when you have a sort of convergence of these colors, that means you have either a 0 or a pole. In this case, you have a simple 0, and you can tell that simply from the color, because if you say start where the red is, like sort of the red ray that sort of points to the right, if you then follow the colors of the spectrum, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, you move in a counterclockwise fashion around the central point. And that tells you that you're looking at a simple 0. If you look at the second figure, it has the same orientation. If you pick one of the red rays and move in a counterclockwise fashion, you see you move through the spectrum in the standard Roy G. Biv sort of order. But there's sort of 3 red or 3 cyan or 3 yellow or whatever rays emanating from that central point. And so you can tell that this is actually a triple 0. The third figure is, you can tell that that's a pole because the orientation is clockwise. So if you start where the red is and follow Roy G. Biv, you have to move in a clockwise fashion. So that tells you that's a pole. And since you only go around one time to go from red to red, that's a simple pole. The fourth image, this is a multiple pole, a triple pole, because you have the 3 red rays, let's say, emanating from the central point and the clockwise orientation. And then in the fifth image, we have a picture of an essential singularity, which I'm not really going to talk about today because those get pretty crazy. So I'm going to talk about these 3 functions here sort of over and over again. All right, so you don't need to memorize them, but it might be handy to sort of take a peek at them. So you can see that f and h are both rational functions. G isn't rational. It's got the sync function in there. All right, but if we take a closer look at f, you can see that there's a quintuple 0 at the origin, that there is a simple 0 at plus and minus 2, and a simple pole at plus and minus 2i. So if we do complex plot of that function, we can see all of those features simply from the color. All right, so like if I start at this point here where I see the colors converging, all the colors come together here, and I start where it's red and I go around Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, come back around, I can tell that has a counterclockwise orientation. And so even without knowing the formula for F, I can tell that there's a simple 0 here. The same thing is true over here. At the central point, at the origin, I have the same orientation. If I start where it's red, red, orange, yellow, green, blue, indigo, violet brings me back to red here. So I have a counterclockwise orientation. So this is a 0. And then there's 1, 2, 3, 4, 5 red rays emanating from that point. So I know that's a quintuple 0 simply from the color. If we come up here, we see more information than was present in the images above. Okay, and so the actual complex plot doesn't just plot the plot the argument with color, but it also plots the modulus of the function by shading. So you can see that represented here in sort of the double legend. So where the shading makes the image perfectly white, that's a point at infinity, that's a pole. So we can tell there's a pole here and here simply from the shading, or you can tell simply from the color. So if we start where it's red and we go Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, and back to red, we can tell that has a clockwise orientation. So this is a simple pole, and the same thing is true down here. So you can tell those are simple poles either from the colors or from the shading. Now with ComplexPlot 3D, we do much the same thing, except instead of shading the surface to indicate the modulus of the function, we use a third dimension. And so you can see the shading here looks pretty much like the one above. The colors are pretty much the same. And then the fact that we have poles here, you can see because you have these two things that look kind of like chimneys sticking up out of the surface. And so that's another way of visualizing one of these complex functions. If in version 12.1, we now have this shorthand notation. If this isn't familiar, this is z going from -3 to 3 plus 3i. So it's a shorthand way of plotting images that are sort of centered around the origin. Now, in terms of options for ComplexPlot and ComplexPlot 3D, one thing you can change is the color function. Now, that's not distinctive to ComplexPlot, but it is pretty handy here. So this is the same function f, okay, plotted over the same domain. But I chose the CMYK color function. And the reason I chose that was I wanted to have, say, the branch cuts stand out. So here, unlike the default color function, at -pi, this is blue or cyan or whatever color that is. And up here where the angle is pi, it's black. And so wherever we have a transition from blue to black, that indicates a branch cut, right? And so you can clearly see the branch cuts in the image, okay, because of the choice of color function. Now, something that is sort of distinctive to these complex plots is the shading functions that are available. And so there's a number of named strings like this that one can use to augment an image. So here I've chosen to show cyclic log abs arg. And what this does is it cyclically shades both in the direction of the modulus or the abs and also in the direction of the argument. And you can see that reflected both in the double legend and then also in the graph. Excuse me. And so the effect of this is it basically, through the shading, makes it look like you have a mesh on the surface, or, you know, both in the, so it looks like you have curves of constant modulus and curves of constant argument, right? And we use log abs because with complex valued functions, you frequently have poles. And so the log keeps the shading, so things sort of look better most of the time if you scale the modulus by the log. We also, again, we have a number of these shading strings. Here's sort of a funky one, cyclic, rem, log abs. So the real and imaginary part here gives you the black curves that you see sort of underneath. And that looks like a mesh based on the real and imaginary parts of G of Z. And the white lines, the bright white lines are like, look like contours based on the modulus or the abs of the function. Here's another one, shifted cyclic log abs. Characteristic of this shading function is around any zero, you tend to get a little color wheel. Okay, like so here you can see three simple zeros. And then around a pole, you tend to get concentric rings like that. Now, if you don't want to do shading, of course, you can always add a mesh, just like in a lot of our other functions. So you can either have a mesh that you put in explicitly, or it can be sort of implied through the shading. Now, complex array plot will be new in 12.2, all right? And so it functions largely like array plot, except it works on complex data. So here we just have, some random complex numbers, and the way they're represented, unlike ArrayPlot, is not with grayscale, but with color. And this is the same shading, coloring scheme and shading scheme that's used in ComplexPlot. So that's not terribly obvious to you from this particular graphic. So here, So here I'm just using some options. I turned the mesh on so you can see the little gray lines between the cells. I changed the color function, and none here turns off the shading. So there's no modular based shading here. But just to show you that this is the same shading scheme as ComplexPlot, I'm going to use ComplexArrayPlot to more or less regenerate the image we saw previously of that function f. So I'm going to make a table here of f on a grid. I wanted it to be a fine enough grid that you could realize that this is the same function or the same plot as before, but not so fine that it's indistinguishable from the ComplexPlot version. So the coloring scheme is the same, both with the color for the argument and the shading for the modulus, right? Now, one difference here is when table hits the singularity or the pole, we get a non-numeric entry in our table. And so that's shown here with that sort of maroon color that we use for either missing values or non-numeric values. And if you want to get rid of that, you can just replace color rules. With color rules, you can replace complex infinity with white. And then this will look pretty much like ComplexPlot. And if you take smaller steps here, you won't be able to tell the difference between this and a complex plot of the same function. Some potential uses for complex array plot. One that I like here is it allows me to visualize the structure of a Fourier matrix. So here's a 16 by 16 Fourier matrix, and I've turned off the shading because I want to highlight a couple of features here. First of all, this has the same color scheme as Abzard plot. So wherever it was purely real and positive, everything's red. So you can see on the left and top margins here of the matrix, you have all red. And then down the center stripe, both vertically and horizontally, you can see alternating red and I guess cyan, right? And so it's alternating positive, negative, through the middle, both vertically and horizontally. And then elsewhere in the matrix, we have complex values, okay, as indicated by the different colors. All right, and then here I use, say, color rules to allow me to replace all the real values with black and all the purely imaginary values with white. So again, you can see the structure quite clearly of a Fourier matrix. I think a nice application of this also is for demonstrating basins of attraction for iterative methods. So I'm returning here to this function we looked at before. So remember, this was the one that was all red, white, and blue with the stars with ComplexListPlot. And remember, all of the solutions lived along one of six different rays coming out of the origin. So there are 6 different angles. So all the basins of attraction, there should only be 6 different colors, okay, based on that, right? And so here I'm using Newton's method for this function, and I generate a bunch of values, and I plot them with complex array plot. So there's really only 6 colors in this picture corresponding to the 6 angles in the image that I showed you previously. But I added a shading function here that I thought was a nice touch because this is going to make some distinctions in magnitude, right? And so even though there's only 6 different angles, there's an infinity of solutions along those 6 different rays. And so the cyclic log-ab shading helps us see that a little bit. Plus I think it looks pretty cool. Okay, complex vector plot and complex stream plot were introduced in 12.1. They're going to be upgraded in 12.2. They're going to inherit the new features that vector plot and stream plot have. And you might have heard Mins talk about that about an hour or so ago. But basically here we're going to try to represent functions, complex valued functions of complex variables, again, just like ComplexPlot. And so to get us started, I've superimposed complex vector plots in the top and complex stream plots below over corresponding complex plot. And so at a point where you have a simple 0, you will see the arrows or the streams either being repelled from that point or being absorbed into the point. If you have a multiple 0, you will see either the arrows or the streams being pushed away and then being pulled back into the multiple 0. And if you have a pole, you'll have saddle behavior. So the streams or the vectors will be attracted in one direction and repelled in another, okay, like this. And if you have a multiple pole, that same sort of thing, you'll have sort of a multiple saddle, so to speak. So this gives us another way of looking at complex functions. All right, so here we're looking at a complex vector plot on the left and a complex stream plot on the right of that same function f that we looked at before. I do want to point out now the color means something different. The color here is a representation of the magnitude of the vector field. Now the vector field is the real and imaginary parts of the complex function f. Okay, so in ComplexPlot, the color was the argument, and here it's really the magnitude of the vector field, more the abs or the modulus of the function. In both cases, I bumped up the vector points and the stream points because this is sort of a busy function. And so you can see this is another way of representing these complex functions. And it's a little easier if you add some labels, which I did with ComplexPlot. So like if you look at these two zeros here, you can see this is a repulsive 0. All the arrows are sort of pointing away from here and pointing away from here. At the center, it's probably easier to look at the stream plot. So you can see the streams being pushed away and being pulled back to the central point, pushed away, pulled back. And at the poles, you can see saddle behavior, right? Being pulled in and then pushed away, pulled in, pushed away, both at that pole and at that pole, all right? So this is another way of trying to visualize a 4-dimensional thing here in only 2 dimensions. Streamlines are going to tend to be discontinuous at branch cuts, like you see here for the log. They're basically being repulsed in both directions here. Some of the options here, again, there's going to be new options that correspond to the new options for vector plot here. So here I'm computing the poles and zeros of this function h, and then I'm going to plot h along with the poles being marked using ComplexListPlot. And so like if you look here, you can see this point here looks like a repulsive point, and this is repulsive and this is attractive, right? But these are 3 simple zeros, you can tell. And then here we have a simple pole because we have saddle behavior where the arrows are being drawn in and then sort of pushed away. Okay, and you can see the same thing over here in the complex stream plot version of the same function. Okay, so something to point out here, to style the vectors or the streams to make them orange, I have to turn the vector color function off or the stream color function off, because the color functions have precedence over stream style and vector style. And so unlike in the past, the streams and the color and the vectors weren't colored. Now they are by default. And so if you want to change it to your own color, you have to turn off the color function. I do want to point out here that the vector fields still look good even in the presence of poles. If you're used to using vector plot sort of in versions prior to 12.2, if you have a singularity in your function, oftentimes the behavior near the singularity dominates the scaling for the whole graph, and the vectors don't always look very good. But in the upgraded vector plot, I think they look pretty darn good. And one of the things that's done here is the arrows all have the same length by default. Now you can change that, but that's a new feature, and that's inherited here in complex vector plot. And so when you have a pole like we have here at the origin, again, you can tell because of the saddle behavior, the graph still looks really good. Another new feature of the vector plots is that the vectors are not laid out on a rectangular grid, but instead on a hexagonal grid, so we can pack more vectors into the same area. Okay. And again, you have the same options here for complex vector plot for changing the vector appearance that you have for the new vector plot options. So we have vector scaling. So if you want the vectors to be scaled based on their length, you can change that. Vector range here is specifying that only vectors with lengths or norms between 2 and 10 should be displayed. And then they're clipped so that they're not shown at all. So you can see near the zeros and near the pole, they're clipped. There's no arrows being shown. The vector sizes here, basically, if the vector sizes are all 1, then that sort of gives you the maximal hexagonal packing. all right? And then 0.1 will be 10% of that. So you can scale the actual sizes of the arrows. So you can control all of that just like you can in vector plot here in complex vector plot. And then let's see, so running out of time. A nice application for this, I think, is a polya plot. So for a polya plot, if you want to do a contour integral, you can interpret the output or the result of the integral as the real part as the work done and the imaginary part as the flux of the corresponding polya field, which is basically just the conjugate field through the curve. So if you look at the red curve C1, you can see it's always orthogonal to the field, to the polya field, and so there's no work done by the field. There is, however, flux through the curve, and so that's a purely imaginary integral, as you can see in the legend. The green curve, in contrast, is parallel to the field, and so the field does do work along that, but there's no flux, and so that's a purely real result. Whereas the blue curve, the field does both work and there is flux through it, and so you get a non-trivial real and imaginary part for that contour integral. Let's see, complex region plot, largely the same as region plot, except you have a complex variable for your domain, and you can plot multiple regions pretty easily. Some nice applications here showing regions of convergence. And I'm going to go a little quicker because I'm running out of time. And then if you want to do complex transformations, a lot of times, people restrict themselves to looking at, where lines go under the transformation or circles go under a transformation. Here you can pick all kinds of stuff. And then finally, complex contour plot. You're going to have a real function here. In this case, it's the modulus of h. So it's a real valued function of a complex variable, and it makes a contour plot for you. And if you can change options, and if you specify more than one function, like absarg here, it automatically suppresses the shading and just gives you basically level curves of the modulus and the argument of h. And then down here, I did rem of the same function. All right, and then to close without running over time, again, it just takes a few lines of code with complex contour plot to recreate Maxwell's well-known image from his treatise on E&M. And so with that, I am done, and I will try to answer any questions that you have. I don't know what's in the beta version. I assume this is all in there, but I don't know for sure. Yeah, these complex things are fun. All right, well, thank you all for coming. I hope you enjoy the complex functionality.